Okay, kids, we're back and we're going to talk about gravitational potential energy. Eventually, we're going to see it in a completely different way. But let's start with a grade 11 view, and we've used this view also when we were studying the energy part of this course. So we're going to talk about gravitational potential energy. So recall now that we learned about gravitational potential energy strictly when it was near Earth's surface. That's it. And we were talking about gravitational potential energy when we had a constant gravitational field of negative 9.8 newtons per kilogram. And we would do things like have an object of a certain mass and it would be lifted against the gravitational field. So we were raising it to a higher gravitational potential energy as its height changed and went through a delta y. And to keep things simple, we usually did it with zero acceleration. So we would restrict our discussion. Maybe delta y would be between here and here. So it's starting up, moving at a constant velocity, moving at a constant velocity in the area we're interested in studying, moving at a constant velocity, moving at a constant velocity, and it might stop up here somewhere. So we really want to be technical about this, and we're talking right in here, definitely zero acceleration as the object is moving. Now, what kind of things would we do in our past work? Well, we would draw a free body diagram with the lift force and the force of gravity, all familiar to us. We would calculate the work done by the lift force, which was the dot or scalar product of the lift force with the displacement. And the displacement and the lift force are both upward, they're parallel, so the cosine of 0 would be 1. We would do some more fancy math work, knowing that the force lift, because there is zero acceleration, is equal in magnitude yet opposite in direction to the force of gravity. So we'd make this transition here. We would put in the expression for force of gravity. And look here, they're all within magnitude signs, right? So we're only interested in the magnitude, not the direction. And we would get mg delta y, which we knew would be the work done by the lift force. And we know that work is change in energy, so we would know that that is a change in the gravitational potential energy. And change in means final minus initial. There you have it. Change in is final minus initial, so I've gotten rid of the deltas and put in that it means final minus initial, which then would mean that we'd have a situation where we would have an expression for gravitational potential energy final, we would have an expression for gravitational potential energy initial, and that led us to our general equation that gravitational potential energy is equal to the mass of the object, the scalar portion of the constant gravitational field strength near the surface of the Earth, and its position y, its height y, somewhere within that gravitational field. So all I did there was a strict review of how we have considered gravitational potential energy in our past work. So what I've done here in this little graph, what I've done is I said, let's take a look at what we've done previously and graph it. Let's graph force of gravity, the magnitude of it, right, which we know is also equal to the magnitude of the force lift. Let's graph it, and it would be constant. The force of gravity on the object near the surface of the Earth is constant because we have a constant gravitational field, and the mass of the object does not change. Fg equals mg. None of those numbers change. So we have a constant force of gravity, a constant force of lift on the object. And let's plot that against the position of the object's y component position. Okay, there you have it. So as the object's y height changes, the force of gravity remains constant. If we were to find the area in here created by this rectangle, bounded by the force of gravity here, bounded by 0 here, bounded by y initial here, and bounded by y final there, we would actually be calculating the work done by the lift force, which is the change in gravitational potential energy. And we've done things like this in the past where we have found the area under a curve and it led to some quantity. And if you think about it, multiplying magnitude of the force of gravity times the change in y is basically doing the dot product and calculating this. Now things have to change. And the reason they have to change, ladies and gentlemen, is that the force of gravity is no longer constant. The force of gravity varies as the position of the object changes. So let me try to draw that for you. So what we did in the past is we were lifting an object off the ground. Now let's consider the Earth here, which I've drawn in green. And let's say we have some space station here, blue S space station, and it starts at a position R1, center to center, all right? And I don't know, maybe Thor comes around or Iron Man, I don't know. And I'm going to listen to the word I'm using. I'm going to lift it, okay? I'm going to lift it against the gravitational field to a new position, R2, center to center. So just like you can lift an object against the gravitational field near the surface of the Earth when the gravitational field is constant, you can quote unquote lift the object against the gravitational field right here to a new position. So very similarly, I'm going to have force lift, right? And now working against it will not be F little g, but F big G, universal gravitation. But we still have to do it with zero acceleration, very important. So instead of graphing F little g versus the y position, we're going to graph the magnitude of F big G, there's the formula, versus R, R being center to center distance between the two objects. And what we get is an inverse square function. If you really want to reduce this to its simplest form, it's a y equals 1 over x squared. And that function looks like this. That function looks like this. So just like I said a few moments ago, if you wanted to find the work done, by the lift force, you would find area. And you would also be finding a change in gravitational potential energy. Well, same thing here, kids. If you want to find the work done, you would need to find the area under this curve right here. But it's an irregular shape. Look, you got a straight line here, straight line here, straight line here, but then the top of it is this function. How do you find the area of that? That's difficult. It's not like before when were finding the area of a rectangle. That's easy, length times width. Now we got to find the area under this function. That's not as easy. Now that is done by something called integration, integral calculus. We don't teach that at high school. I'm going to put a link to a video it's optional, that you might be interested in looking at about integration. But since we don't have all the calculus in our minds right now, we need to find this area in sort of a fake, well, not fake's a bad word, a different type of mathematical reasoning to allow us to find the area of this irregular shape. Ideally, we would all know calculus, right? And we could do this. We could take this function, integrate it, and find the area. One day you will be able to do that. I have no doubt of it. That day is not now. So, final recap here. We're in a quandary. We need to find this area of an irregular shape. Why? Because the gravitational field is variable. We've been used to constant gravitational fields. That is no longer the case. Well, if we're going to find the work done by lifting an object to a higher orbit through a variable gravitational field, and therefore a changing gravitational force on that object as we lift it, we need to really become familiar with this function right here and look at its limits, which I think you may have started in calculus or some other math courses. So as r approaches 0, so as the denominator approaches 0, the force of gravity approaches infinity, which makes sense. The closer two celestial bodies are to each other, the stronger the gravitational force between them. Next, as r approaches infinity, as the denominator approaches infinity, the force of gravity between them approaches 0. The further apart these objects are from each other, the weaker the gravity. The force of gravity is dictated by the fact that the gravitational field, as you get further and further and further away from the mass that creates that gravitational field, gets weaker and weaker and weaker. The gravitational field of the sun at a distance where maybe Mercury is the closest planet, stronger gravitational field there from the sun compared to the gravitational field of the sun where perhaps we're at the orbit of Neptune or something like that. Much further out, much weaker gravitational field. All right, hope that helped. Now, as I mentioned, since we don't know calculus, I'm going to have to try to explain this to you in sort of a backdoor way. So let's take a little play out of Shakespeare, and we're going to have not a Shakespearean aside here, but a little mathematical aside. Let's pretend here that if the magnitude of the force of universal gravity was linear, we're pretending here, if it was linear, if this red line is what the function looked like, okay, it's not true, we're pretending, okay, so at this point here, we would have gravitational potential, excuse me, force of gravity at R1. So this point right here is force of gravity at R1. This point right here is force of gravity at R2. So I've labeled this point right here R2, force of gravity 2. That's that point right there. And this point right here I've got as R1, force of gravity 1. And if we wanted to find the work done to lift an object from radius 1 to radius 2, we would have to find the area under this red line here. The area under this red line. That's what we would have to do. And you could do it. You could split this into a rectangle down here, right? And maybe a triangle right there. Or what you could do is say, look, I want to keep this really simple, and I want to find an area which is rectangular. And the height that I'm going to choose is going to be the average between force of gravity 1 and force of gravity 2. I'm finding the average here, cap it off there, and I know that this blue simple rectangles area would match the area under the red line, which is more of an irregular shape. Well, the beauty here is if it's linear, it's easy to find this average right here. It's very easy to find the average. It would be what we call an arithmetic average. You take FG1 plus FG2 and you divide it by 2. So basically you're taking this value right here, FG1, this value right here, FG2, you're adding those two values. You're adding FG1 to FG2. There's two terms. You're adding them, and you're dividing it by 2. And that would give you the arithmetic average, this height, if you will, right there. So finding the area would be simple. Take that average, which we have right here. Take that average. That'll give us this side of the rectangle, right? This term right here is this side of the rectangle. Multiplied by this side of the rectangle, the base here, which would be R2 minus R1. If from 0 to here is R2 and from 0 to here is R1, then what we got left in here is simply R2 minus R1. And we could find the area. And this would work if the function was linear. Is it linear? No. But it's given us a very good idea to move forward without calculus. Bear with me, please. The function for universal gravitation is inverse square function. It's not linear. Look at it. I got it here in purple. It's not linear. All right. The area is quite irregular. Straight line, straight line, straight line, but the top is the function. The top is the function. But we can still label some important points here. We can still label that point there, and we can still label that point there, and we can get an ordered pair from there, right? That would be R1, FG1. We can still get ordered paired like the other example we did. And right here, we would have R2, G2, and of course its magnitudes. So we can still get ordered pairs, all right? So by taking a cue from the averaging that we did before when we were pretending it was linear, we can use a different kind of average. The averaging that we can use is called an arithmetic average. And the arithmetic average, excuse me, not an arithmetic average, that's what we just used. We're going to use I correct myself, a geometric average. Here is the geometric average. Instead of adding the two of them and dividing by 2, you multiply the two of them. So you take this part of the ordered pair, you take that part of the ordered pair, you multiply them together, and then you square root. And that will give you some average height in here. And then the base remains the same, R2 minus R1. So we're finding a different way of finding the average cap, the average height to complete our rectangle, and that is done using a geometric average. There it is. So let's put in the expressions for the force of gravity. So this is what I've done right here. I've put in the expression for Fg1 magnitude. I put it in, G, mass of the Earth, mass of the satellite, all over R1 squared. I put in this expression, Fg2, G, mass of the Earth, mass of this satellite, all over R2 squared. And this bracket, R2 minus R1, the base of this imaginary rectangle that we're finding the average of, it remains the same. Let's continue with the mathematics. Let's take a look at this. We're going to multiply these two together. G times G, G squared, but you're finding the square root of G squared, G. All right? Mass of the Earth times mass of the Earth, mass of the Earth squared, but we're finding the square root, mass of the Earth. Mass of the satellite times mass of the satellite, square them, but you're finding the square root, so it's just mass of the satellite. Then R1 squared times R2 squared would be R1 squared, R2 squared, but we're finding the square root of both of them, so it's a denominator of R1, R2. And the bracket for the base of the rectangle remains. This remains R2 minus R1. That remains. What are we going to do next? Well, next we're going to do some distributive multiplication. We're going to take this term that we just came up with and multiply it onto the R2, and then multiply it onto the R1. Okay, that's what we're going to do here. All right, let's do our multiplying here. We're going to multiply into the R2. So when you multiply this into the R2's cancel. You're just left with an R1, and there's the term. When you multiply into here, you've got a negative sign, so you got to keep the negative sign. But you multiply the R1 times this, the R1 cancels, that R1 cancels, and you're left with an R2. So you're now left with this. And remember, this is finding the area under that graph, which is the work done by the lift force, which is also the change in now big G, the change in universal gravitational potential energy. We're changing here, all right, big G. Now, we have an issue here because delta EG means EG2 or final minus EG initial or 1. It doesn't matter what we use. But look at the setup here. Instead of it being second situation minus first situation, it's reversed. What? That's not what delta means. So we have to do a little bit of mathematical sleight of hand here, and this is what we're going to do. What we're going to do is we're going to bring this term with its negative sign out front, okay? And remember what delta means. It means subtracting. So I'm going to put that in here. But I have to have this term here be positive. Look at it. It's positive. So the way around that is take that term here, put a negative sign in front of it. Negative times negatives gives me the positive I had originally. This had a negative sign in front of it originally. It stays. Now it's in the classic EG2 minus EG1. EG final minus EG initial. Look, second situation R2 minus first situation R1. But this has really changed the ball game here, because then this leads to this situation right here. The universal gravitational potential energy then has to be a negative value. Look, a negative value, subtract a negative value. By its very definition, here's an equation you need to put in your equation sheet. Universal gravitational potential energy is a negative value by definition. And that's going to have a lot of mathematical ramifications as we move forward. Take your time, think about this. I'm telling you, universal gravitational potential energy, by definition, is negative. So what I've done here is I've plotted this new function we have, this new equation for universal gravitational potential energy. It's always negative. There, I graphed it. It's in red. All right. So if we were dealing, for example, with the surface of the Earth, if you had an object that was sitting at radius of the Earth, just pretend it's the Earth for this green situation here, radius of the Earth would be right there, and at that point right there, you would have EG, the universal gravitational potential energy of an object when it was on the surface of the Earth, or it could be the surface of the moon, anything. So that spot right there is telling you that when an object is on the surface of a planet, a moon, what have you, surface of the Earth, it has a negative gravitational potential energy. Let's take a look at this. As r approaches infinity, so as you get further and further and further away from the object that we are investigating through its gravitation, the gravitational potential energy, what it does is it approaches it as r approaches infinity, it approaches zero. So look, r gets bigger and bigger and bigger. This approaches zero. It's like an asymptote. So think about that. The further you get away, your gravitational potential energy approaches zero. What this is saying is if you could get to infinity, wherever that is, at r equals infinity, that is where we are defining gravitational potential energy, universal gravitational potential energy, to be zero. It is defined to be zero at r equals infinity. When we had the gravitational potential energy near the surface of the Earth, remember the old E little g is equal to mgy? Remember the previous version of this? We would say, oh, gravitational potential energy near the surface of the Earth, it's zero at zero height, at y equals zero. That's where we defined the zero reference point. We can't do that now. So we are defining the zero reference point for where universal gravitational potential energy is zero as where it is when r equals infinity. Kind of technical. Let your head wrap around this for a while, but this is the way we have to move forward mathematically. The other strange thing about this is universal gravitational potential energy equaling zero, which occurs at r equals infinity, wherever that is. This is very much a process of the mind. Okay, it's mathematics here. All right. This is your zero reference point, but it's also your maximum gravitational potential energy. It never gets bigger than zero because it's negative. Try to wrap your mind around that. So where does that all lead us? It leads us to this. In the past, we would do questions where we would have a constant gravitational field like this. And we would use the law of conservation of energy, right? We would use this where mg was mgh, right? Now we still want to do that, but the gravitational field is not constant, right? But we still want to use the law of conservation of energy. We still want to do that. This is still true. The law of conservation is still true, but EG is now different. It's negative. It's negative G, mass of one object, mass of the other object, all over R. So we still want to use a law of conservation of energy, but we want to use it with this new expression, which is negative. All right. So today I'm going to have you watch this video I just created, read a little bit about it in the textbook. I'm going to have you look through a video on differentiation, excuse me, integration, I beg your pardon. All right. Let this kind of sink in. Let it kind of roll around in your mind. Maybe have a little slap chat, TikTok video, talk with your friends. I don't know what you guys do. Okay. And tomorrow I'll give you some questions on it. Let this sink in. Okay. Thank you, everybody, for working hard. I really appreciate it. Take care. Bye bye.